I will introduce Professor Wenwu Wang. Professor Wenwu Wang is a professor at University of Surrey. He has already co-authored over 300 papers in machine learning and signal processing. He is the author of Audio LDM, SemantiCodec, and PAN, which are very, very famous papers in the recent codec domain. And his presentation title is NeuralAudioCodecs, Recent Progress and a Case Study with SemantiCodec. Let's welcome Professor Wang.
Thank you. Thank you. Thanks for the introduction, and also thanks for the invitation. So today I'm going to share with you some of our recent work on NeuralAudioCodec, in particular SemantiCodec, which is developed by our excellent students, Liu, together with other PhDs and colleagues. Here is the outline. So I start with the background about audio codec and NeuralAudioCodec, just to provide some information on how this is done historically and why we need NeuralAudioCodec. And then we discuss the limitations of current NeuralAudioCodecs and propose our method to address these challenges. And finally, we're going to show the result and also conclude the talk with a discussion on future work. Audio codec. So what is audio codec? Of course, in general, there are also other data like image and video. So we also have image and video codecs. But here we are focusing on audio codec. So codec is the term for compressing or decompressing, or compressor or decompressor, right? So how this is done historically? Historically, this is done using techniques, for example, linear prediction. You can directly play with the waveform. You try to use a simple mathematical model based on the previous time samples. You predict the samples in the future, right? So you use such simple models. Or you could use other techniques by converting the data into the time frequency domain using techniques like discrete cosine transform or modified discrete cosine transform or subband analysis. You try to convert data from time domain to the frequency domain or time frequency domain. And then you figure out which time frequency point of the data can be discarded based on the ideas like psychoacoustic masking. Because humans' auditory system is not so sensitive to some of the frequency components in the data. So that's the basic idea, how we can use the perceptual redundancy to remove the redundant data, right? So well-known codecs, for example, MP3. MP3 is the codec under so-called MPEG standard, right? So what's the key idea here? So you use, this so-called psychoacoustic masking, auditory masking, right? You try to figure out the energies at each frequency component in the signal, and then you figure out which frequency component is masked by the neighboring frequency component or other frequency component in the signal, so that you can remove that particular frequency component. So this is type of lossy coding, where essentially the signal cannot be perfectly reconstructed. It's different from lossless coding, where you can reconstruct the signals. Right? For example, one of the well-known lossless coding method is used in this zip file. Right? We all use compress the data zip file. You can perfectly reconstruct the data, but for lossy coding, you cannot actually reconstruct the data. So this is where widely used in audio coding for transmission, for storage, for playback. But one of the key challenges here is that we want to compress the data to as small as possible, but at the same time to reconstruct data, to as close as possible to the original signal. That's the key challenges, right? So this is actually a dilemma because these two objectives are conflicting. So if you throw away data, you are likely to introduce artifacts into the signal. So you cannot actually get both right. So this is also the design objective. You can see a lot of textbooks talking about how to compress the data, how to reconstruct the data. So that's the main effort in many textbooks. So with the conventional audio codecs, we get the advantage. For example, we can explain which component in the signal, which frequency component in the signal we throw away. We understand very well on that. So this is one of the main advantage we call explainability, right? But the disadvantage of these conventional audio codecs is that the compression ratio is already reaching to a certain limit. And so that's why this NeuralAudioCodec comes in. NeuralAudioCodecs, as already discussed in the previous talks, we use this machine learning system to design the encoder and the decoder, or in other words, compressor or decompressor, right? And then you can actually, now the design choice is what type of encoder and decoder should be used, right? There are a lot of talks talking about that. Some people are using GAN network, as in this sound stream, they're using GAN network, right, to do the compression, decompression. And coupled with this vector quantization, this is the k-means techniques to throw away the information, redundant information from the encoded vector, which is Z here. And then this encodec or discrete are actually built, and also hypercodec actually, are built on sound stream. And a speech tokenizer, for speech, for example. So the key research questions here, what type of encoder and decoder should be used, right? So this is a lot of work around that. But again, back to the original objectives. The key here is that we try to compress the data to as small as possible, but to maintain the quality as high as possible. So that's always the objective. So apart from the compression and decompression, which is very popular for, or is one of the key components in any communications, there's also other reason for developing NeuralAudioCodec. So one of the reasons, as explained in the previous talks, is that we can actually tokenize the audio data so that we can use large language models. We can borrow some kind of knowledge from large language models to do a lot of downstream tasks. So that's actually one of the advantage for converting, for developing this NeuralAudioCodecs. Another advantage is that we can actually combine this with text by using text as condition, so that we can build models for text to music, text to audio, or speech models. So the third advantage would be, for example, we can actually develop these joint foundation models for compression or understanding, like this recent work on audio palm, right? We didn't mention here, but there's work on that. So there's a lot of advantage of doing that by building this NeuralAudioCodecs. But the limitations of the current NeuralCodecs is that one of the limitations is that usually the token rate is pretty high. We explained earlier that NeuralAudioCodec has an advantage working with large language models. Because we tokenize the data, we can then use large language models to process the tokens. But the current or previous NeuralAudioCodecs often produce very high rate of tokens, which means that the number of tokens per second is pretty high. For example, here we have example for the DAC, which is given 600 tokens per second. So why this cause problem? Because when we actually use this combined with language model to process tokens, then the inference complexity becomes high. The computational complexity becomes high, and also the speed, right? So that's cause problem. And another thing is that the current NeuralAudioCodecs, the reconstruction quality is often is poor, especially for low bit rate. Low bit rate means bit rate less than 1 kilobits per second, and often the performance was not satisfactory. So that's why these two big challenges. Another challenge is actually, if you look at the current neural audio codecs, that the semantic information given by these tokens from this previous audio codec, neural audio codecs, is not very good. We compared several neural audio codecs that the semantic information in the tokens actually have been lost. So the motivation of our work is that we want to actually develop audio codecs, neural audio codecs, which has lower token rates and also a better reconstruction quality at a lower bit rates, especially below 1 kilobits per second, and of course improved semantics information within these tokens. So that's our motivation. This comes the SemantiCodec, and as I discussed earlier, so the key here is about the design of the encoder and the decoder, right? The decoder, people use the GAN network like this, the previous neural audio codecs. But here, the several contributions here. One is we actually try to leverage the excellent performance of this AudioMAE as encoder, because this AudioMAE captures this semantic information very well. Later on, I'll show you an example why this one could be better than other encoders. So this actually leverages this so-called semantic learning. There are different techniques out there. One is contrastive learning, for example. Contrastive learning could be either leverage this positive or negative samples, you try to distinguish them, right? But it could also be so-called masked language modeling, where you mask the data and then you learn the labels. This is a discriminative method, but there's also a method about reconstructing the missing or the masked component within the signal. So here we are actually using this AudioMAE because it provides or it retains good semantic information from the audio signals. So that's the reason. Another thing is that it's a model which is used to reconstruct the data. So the reconstruction performance is also very good. So that's why we are using this AudioMAE. And of course, to create these code works, which we try to represent the original audio data. So we use this vector quantization k-means algorithm, right? And or you could also use other vector quantization techniques. But here we actually use this to cluster the embeddings from the AudioMAE. And here we have this so-called two encoder structure is concatenated these two audio encoders. One is this k-means based. We create this semantic code work. Another one is we call an acoustic encoder. So it's a combination of semantic encoder and acoustic encoder. The semantic encoder is trying to capture the semantic information. The acoustic encoder is trying to capture the acoustic information or the residues or the detailed information from the audio data. So that's the encoder side. The decoder side, we are actually using this diffusion model. When we were writing this paper, this is probably the first work that is using the diffusion model to do the as the decoder. So that's the difference, right? And yeah, there's a lot of details here, but you can read the original paper about. Just a little bit more about the AudioMAE. So AudioMAE is a self-supervised pre-trained model. Essentially, it's like leveraging this VIT, which is very well known in image processing, the vision transformer. Actually, what they are doing is that you take this For example, in our case, the spectrogram, you mask some part of the spectrogram, and then you learn a model to reconstruct the masked part. Yeah? So here the learning objective is we want to reconstruct that. But it turns out actually the embeddings learned by AudioMAE contains this semantic information. We compared this AudioMAE against VAE embeddings. You could use a VAE, variational audio encoder. We found actually that this is the scatter plot for the embeddings from VAE on the left, and on the right is AudioMAE. You can see that the different colors means that the embeddings from different sound classes. You can see that the AudioMAE distinguish very well in terms of the sound classes. You can directly use these embeddings to do classification, for example. So that's why the semantic information, about sound classes in this case is retained very well. And we also compare with other latent embeddings. This one seems to be doing better, right? So that's about the encoder. The decoder we are using is a diffusion model. Most of you probably are very familiar with diffusion model. It essentially contains forward and reverse diffusion process. The forward process, you try to turn data which is of unknown distribution. So you don't know what exactly is the distribution of the data. But you can actually turn that one into distribution, which in our case is noise, right? We know the distribution of noise. We actually turn this unknown distribution into known distribution, which is Gaussian in this case. And then we train a neural network model to try to predict or to reconstruct the data. Basically, we predict the noise added in each step. So you try to optimize the model parameters. In our case, we're using this UNet or transformer UNet, this type of neural network architecture. And then we should try to use that to predict the noise added in each step, right? And then we can actually reconstruct the original audio data. So we're actually working this in the latent space. Instead of directly working on like audio samples, we are working with latent vectors, which means that one of the main advantages is that computationally it's much more efficient, right? So this is, and also in terms of the generation quality, is also very good. Here is a figure we borrowed from a tutorial paper in Europe. So basically, we are working in this latent space. So in the paper, there are a lot of details. I won't go into details in terms of which loss function we're using and how we set up the system. And now I come to the evaluations. We are using the performance metrics to do with reconstruction quality. For example, MER. This is measure the difference between the reconstructed spectrogram as compared with the original spectrogram. We also use the short time Fourier transform distance. That's also compare the two spectrograms. And then we also have this objective perceptual quality measures, which is VRS QOL. This essentially measures the MOS, mean opinion score. So we also actually perform this word error rate, that for speech, okay? And accuracy, when we evaluate the semantic information, we are using this audio classification task to measure how good it is in terms of using the audio embeddings produced by the NeuralAudioCodecs for classification. And we also perform this listening test using this Machira test. This is very well known in perceptual evaluation. The data set we used for training, you can see here, including both speech, like speaker speech, meaning song data set, that's for music, and also MetaDB and MuseDB. That's all for music, right? AudioSet is for general sound, and VGG sound is also for general sound. Wave caps also for general sound. And the baseline we compared, including encodec, discrete codec, and hyper codec, which already discussed earlier. In terms of the size, you can see that the model size. And the model size of SemantiCodec we developed is about 75 million parameters. And here we performed these evaluations in terms of reconstruction quality, semantic information, and subjective evaluations, right? And these are the data set we used for performance evaluation. And for subjective evaluation, we used 10% of the total evaluation data. So in here we have about, for example, 25 music tracks, 30 speech recordings, 50 general sound samples. We have 10 raters, 10 human listeners we recruited. And now I show you some result. This is the reconstruction quality. Here you can see that with SemantiCodec, when the bit rate, usually the bit rate is much lower. Here, we can achieve the bit rate as low as 0.36 kilobits per second. You can see here the if you look at the VIS score, which is about 3.17, if you compare with the DAC, for example, so there are different DACs here. If you look at the DAC at, for example, 1.41, the score you get is 3.13. So which means that even though that the bit rate of our SemantiCodec is very low, we actually still get very good reconstruction quality. Is even better than other codecs with a higher bit rate. Okay, that's the main message. So it does very good job in terms of reconstruction. In terms of semantic information, now we can see that because we performed on different audio classification tasks, ESC for general sound, we also performed on pitch pitch recognition and some other tasks. For example, speaker counting, this is a different voice imitation, for example. You can see that the performance here, again, SemantiCodec does much better in terms of maintaining the semantic information about the sound classes. Other codecs, you can see that the average ACC here for DAC, the performance is very poor actually, and our codecs maintains very good quality in terms of capturing the semantic information about sound classes. So okay, you can see the result here. So that's the key message. So we also performed ablation studies in terms of the design choice, and here we compared, variable vocabulary sizes opposed to fixed vocabulary sizes. And in our training, we have, I didn't see the details here, but actually we have multiple codeworks for speech, music, and general sound. And each codework has a different size in terms of the number of code words. For example, we have roughly 1,000 code words. We also have like 16,000 code words. So we have 5 different code works for speech, 5 different for music, as well as 5 for general sound. So we actually, when we do the training, we randomly pick up the code works, and we compared this training strategy against, the training strategy using the fixed code codebook size. Yeah. And we also compared between using the frozen semantic codebook and the learnable ones. So that's also the result, which shows that by frozen the codebook, especially the one we already obtained, is better in this case. There are some other ablation studies. For example, in our when we train this latent diffusion model, the decoder, we actually used this classifier-free strategy, which some of you might be very familiar with. Basically, the idea is that you actually add the conditions, right? Because when you use the diffusion model to reconstruct data, essentially you're learning this posterior probability. You add the condition into the condition is the embedding extracted from the audio data. But you can actually throw away the condition. Here we are using the parameter. For example, here there's guidance scale, which tells you how much condition you added into the model training. So in this case, we found that by actually adding condition together with unconditional generation, is the best strategy, especially the guidance scale roughly at 2 or 3. That's a good choice. And we have also performed some other ablation study. I won't go to the details, but if you look at these spectrum plot, you can see the quality of the reconstruction using the different codecs here and different kilobits per second in terms of the bit rate. SC is a semantic codec we developed. You can see that it does a better job as compared with DAC and encodec EC and so on. And here we have a bit more information about the reconstruction quality, which is the horizontal line, and the vertical is actually the semantic information in the audio codec in terms of the classification accuracy from from the code word we used, right, for performing the classification. You can see that the red one corresponds to SemantiCodec, which provide the best information in terms of semantic information. At the same time, in terms of reconstruction quality, is also on the top end. And the bit rate is lower. So this is a very good audio codec. Some of you might not be familiar with. You should actually try this and also compare with some of the other models to see how good it is, right? Here we also have the mature scores given by humans. The blue one corresponds to the semantic codec we proposed, and the green one corresponds to the DAC. You can see that the mature score is much lower than the semantic codec. Of course, here we didn't compare with some of the other neural codecs. It's because most of the neural codecs, the bit rate is much higher. We are actually focusing on if the bit rate is much lower, can you still get very high quality reconstruction and also retain the semantic information? Yeah, sorry. There are a lot of more demos on the website. I would suggest you to go there and have a listen. There are many other different type of sound files, quite different from this one I just played, including music like a vocal or drum sound, piano sound, many different type of sound there. Okay, time is running out, maybe. So I want to conclude and discuss future work. So we have presented the semantic codec which produces audio tokens of more semantic Van Noyer token rate, more semantic information, and also works for any length audio because we have a mechanism that is able to process any length of audio, and so it's provide a very good ultra no bit rate audio codec. And the future work, we haven't actually evaluated the relationship between the semantic of the tokens with respect to the language modeling performance. So that's quite interesting to study, actually. Another thing is that we haven't studied the shortened audio token sequences, how this elevate these language modeling robustness issue, right? And we could also specialize this because we are developed for general sound, but you can actually specialize to the task you have or the data you have. So I would like to thank Jorge to provide most of the slide here and also the funding here. So this is a takeaway. If you are interested, just read the paper and source code out there, more demos out there. And thank you very much.
Thank you, Professor Wang, for the very good talk and a very good work. Any question from the audience? Yeah.
Dear Professor, thanks for your excellent presentations. And I have several questions. The first one is that I wonder to know what is the generation efficiency of this codec? Generation efficiency means that generate 1 second speech using how many seconds?
And in terms of my understanding is if you use GPUs, it's real time, which
real
means
time.
that generating 1 second is less than 1 second.
Okay.
So, yeah.
But for CPU?
No, we only used one.
One.
So in this audio codec, we used 2, but because we use the diffusion model, the data diffusion audio RDM, we use the audio RDM 2. So I think 2 maximum enough actually. So you could also use just 1. Yeah.
Oh, okay, thank you. Another question is that I wanted to know what is the model size of the audio codec?
Well, actually, I already mentioned it's in this case it's 75 million parameters. 75 million.
Okay,
so
thank you.
Is I think it's comparable with the one of the other I mentioned earlier. There's one is here, like DAC is 74 million.
Oh, okay.
You can see that, yeah, in codec is 23 million parameters.
Oh, okay.
Yeah.
The last question is that this codec consider the latency. Do you consider the latency in this codec for real-time communications?
Yeah, I mean, I guess again, it depends on what type of devices or computing facility you have. If it's a GPU, as I said, processing 1 second is less than 1 second actually. Processing 1 second data is less than 1 second, so it's real time. But we didn't really measure the precise latency. It was trying to see how exactly it is, but in terms of my understanding that so it's real time if your machine is a GPU type of machine, so it's real time. But if you are using other machine, then it won't be real time. Yeah.
Oh, okay.
So
thank
the
you.
latency will be getting higher. Yeah.
Okay. Thank you, Professor.
Thank you.
Any other questions? Yeah.
Thanks for a great talk, Professor Wang. I have a question about using codec for emotion recognition. So recently, we benchmarked various audio encoders for music emotion recognition on both regression and classification. And among the audio encoders, we used two codecs. One is the encodec and one is the DAC. And we surprisingly found that the two models significantly did a worse job than other audio encoders like self-supervised model and contrastive learning model, and also the VGG-ish. So we think that it might be because of some emotion-related music details got lost during compression and decompression. So I'd like to know, do you agree with this explanation, or do we have any other explanation, or do we have work or example to demonstrate that codec actually work well in emotion recognition? Thank you very much.
I suspect you're right, actually. If you look at one of the results, this table, here you can see that for DAC, for example, we tested 6 kilobits per second, 1.41 kilobits per second, also 0.36 kilobits per second. That's the average classification accuracy we achieved using the various data sets. And if you look at, there are also music data set there. So it seems like the codec or the code word they produced. I didn't go to the details of these codecs, but there is a strategy they used for very low bit rates, which might be harmful for the performance. So I think it's worth going back to that to see what happens, because there's, we briefly mentioned in the paper about that. That's why, there's drop in terms of the performance there. But actually, SemantiCodec is doing a good job. Maybe you should try.
Yeah, we should try that. Yeah, thank you very much.
Yeah.
Any other questions? Okay, we will take the final question because the time is limited. Yeah.
Hi, Professor Wang. Thanks for the great talk. And I want to ask actually, I just want to ask a very probably stupid question. And if we're using, for example, Hubert or WebLM, because they actually don't have any assumptions or supervision data. So if we're simply using this WebLM to do traditional k-means and then to extract this ID and this discrete ID and apply a vocoder on top of this discrete ID, whether we could still reconstruct the waveform from the audio data, because we know that it actually works for speech data, right?
You mean directly perform k-means? Yeah.
Yes, using k-means to do quantization, to quantize the hidden vectors extracted from audio data, then trying to reconstruct it using a vocoder.
I think it still works. That's actually the convention in how this is done.
Yeah.
But the problem is that some of the details will be missing depending on how good is the acoustic. In our case, there's SemantiCodec, but also acoustic code. The reason we are doing that is, we want to capture the semantic information as well as the detailed information. So this is also one of the main objectives in majority of the audio compression algorithms. How to, to best retain the information from the data while compress the data to the smallest size as possible. The techniques you are mentioning, it still should work, but I doubt this will give you the best reconstruction quality, because that's the objective in telecommunications. We want to achieve the best reconstruction quality. But of course, if it's not for communication, it's only for classification, then the semantic information becomes more important. For example, the early audio codecs like RPC, linear prediction coding, where it does a very good job in terms of capture the key information there. If you use for classification, it's fine. But if you want to use this to, for communication purpose, then people need to hear the sound. The sound quality will not be so good, actually. So there's always kind of a trade-off there. You want to maintain the semantic information. At the same time, you want to achieve the best reconstruction quality.
Yeah, the reason why I ask is that because we're actually looking for a kind of this secret token could apply both for various audios, for sound, music, speech, and then it could be easy to compatible with large language model. So, and as we know, yeah,
I agree with you that there's also difference. I didn't explain clearly here. So if you look at these three plots on the bottom right, this is for three different type of audio data. Not this one. Let me check whether. Oh, I didn't show here. So we have a comparison in terms of speech, music, and general sound, and we found that this codec does better on music and speech, not as good on general sound. The main reason might be for general sound, the dynamic range is quite different. Also, the frequency range are much also wide. Especially the content, the frequency content, the spectral content are quite different. That's probably the codebook we designed is not able to fully capture all this information. And so that's why it does not do as good job as compared with speech and music when we apply to general sound. Yeah.
Okay, thank you.
Let's thanks Professor Wang again.
Thank you very much.